Okay, so welcome back to the next class of complex analysis. In the previous class we started very important concept called residue, and if a function has a simple pole, then we find the residue of that function fz at z0 can be represented as limit z tends to z0 z minus z0 f of z. That was the recipe of that was the recipe of that we know. Now we extend this and try to consider what happened if the function has singularity of order n or order k. So if the function has a singularity of order k, then this function fz has to be represented in this particular form, z minus z0 to the power of k plus a minus k plus 1 z minus z0 k minus 1 plus a minus 1 z minus z0. This is the analytic part, principal part, and the analytic part is a1 z minus z0 plus a2 z minus z0 square and so on. So this expansion is valid when the function has a singularity at z equal to 0 and the pole is of order k. So that is the pole of order k. So now the question is how to deal with these things, how to find out. My goal here is to find out this quantity a0 somehow. So the first thing that we can do, that we multiply z minus z0 to the power k to both the side. If I do z minus z0 to the power k, we multiply with the fz, then the first term will be a minus k in the right hand side, second term will be z minus z0 a minus k plus 1 plus so on. I have a minus 1 multiplied by z minus z0 to the power k minus 1 and plus a0 z minus z0 to the power k plus a1 z minus z0 k plus 1 and so on. I just multiply. In the previous case I multiplied z minus z0. In this case, if I have a pole of order k, I just multiply z minus z0 to the power k to the entire function, and the expansion of the function should be something like this. Once I have the expansion of the function, then still this quantity is sitting here which I need to find out. So what we will do, I need to reduce these things. So in order to reduce these things, best way to derive the left hand side, to make a derivative of left hand side with respect to z up to k minus 1 times, so that all these things will gone. So that is k minus 1 z k minus 1, right hand side is z minus z0 to the power k f of z. Once I make a derivative with k time, all this term will go away, only term that is here should be k minus 1 factorial a minus k. So every time when I make a derivative, this power will come, and for that k minus 1 factorial term will be there. Then I will have one term, analytic part, I will have a0, and again this k minus 1 k into k, k into k minus 1, and all these terms. So, here, so I will have factorial k here divided by factorial 1 z minus z0 to the power z minus z0 and so on. The right hand side I will have this term. Now, what is the next thing? Because I already have this term in my hand. Now, if I put the limit at z tend to z0, so all the analytic part will go away. If I do, so let me do it here. So, I will do that. So, limit z tends to z0, this quantity k plus 1 k minus 1 dz k minus 1 z minus z0 function of z. If I do, then in the right hand side I only have one term, which is k minus 1 factorial a minus 1. From that I can now extract a minus 1. So, a minus 1, which is my residue, is now extracted for a function which has, so a minus 1 will be how much? A minus 1 will be how much? 1 divided by k minus 1 factorial limit z tends to z0 d k minus 1. This is my recipe. This is my recipe to find out what is my a minus 1. Once I know the function has a singularity at z equal to z point with pole of order k. So, I have two formula in my hand, and if I write these two formulas side by side, this formula will be something like this. So, let me write it here. So, residue f z is something limit z tends to z0 z minus z0 f z. This is one recipe when we have a simple pole. Residue f z is 1 divided by k minus 1 factorial d k minus 1 dz k minus 1 z minus z0 to the power of k f z. This is my recipe 2. Two recipes in my hand. So, I am going to use to find out the residue. So, now directly go to the problem. So, let us start with few simple problem, and then we will try to understand how these things are working. So, first example 1, f z is equal to 1 divided by z minus 1 whole square z minus 3. Suppose this is the thing. I need to figure out the residue at z equal to minus 3. So, how many singularities are there? Singularities. So, first I need to find out singularities. One is z is equal to 1, that is the first singularity, pole of order 2. So, here this singularity is not a simple singularity, it has a pole of order 2. However, second singularity is at z is equal to 3 point, at z equal to 3, but it is a simple pole. The formula suggests that if it is simple pole, the formula is quite straightforward and simple. So, let us try to find out first the residue at 3, and mathematically it should be written as residue of the given function f z at 3. What is the recipe? I will multiply, I will take the limit at z tends to 3, multiply the function z minus 3 the function here is 1 divided by z minus 1 square z minus 3. I will do that, and it will cut here and here, and now I put the limit to the function. It will be 1 divided by 3 minus 1 whole square. So, I will find 1 by 4. So, my residue at 3 is comes out to be 1 by 4. What about the other residue? Because other residue is at z equal to 1, but having a square term associated with that, that means it is not a simple pole. So, I need to use the second recipe, this one. So, again residue of fz at point 1 is how much? I need to take the limit z tends to 1 and then take a derivative, first order derivative, because since k is equal to 2, 1 divided by 2 minus 1, it is 1 factorial. So, this term is 1. So, here I will put 1. So, that is why I did not put anything, but it will be the first order derivative, because the derivative of order should be k minus 1 if the singularity has the pole of order k. So, here pole is 2. So, that means I need to do the derivative 1 less than that. So, first order derivative. So, which quantity I need to derive? Z minus 1 multiplied by the function is this. Function is this. So, now this quantity will cancel out, that is why we multiply that, and then I need to make this limit z tends to 1, and then derivative of this quantity is 1 divided by z minus 3 square. Once I make 1 divided by this thing, so minus 1 term will somewhere come here because of this derivative. So, I will have this. So, now I will put z, the value of z here. So, here minus of 1 divided by value of z here is 1 minus 3 square, which is minus of 1 by 4. So, first case my residue was 1 by 4, in the second case the residue comes out to be minus 1 by 4. Okay. This is the first example, and blindly I am using these things. So, I am getting some results. So, let us do similar kind of problem, few problems, so that you are familiar with whatever the residue you are getting. So, next problem is again quite straightforward. So, example 2, the function is given as, let me check once again, yeah, 5 z square minus 4 z plus 3, the numerator, and the denominator, the function f z, by the way, it is this, and it is z plus 1, z plus 2 and z plus 3. Okay. This problem looks very straightforward, because whatever the value are given in the numerator all have a simple pole. Once we have a simple pole, the problem is very simple, since there is no derivative is required and all these things. So, let us do that thing and try to find out. So, this is some sort of exercise, and it is a good exercise. So, let us try to find out residue of this function f z at one point. So, where the residue? Mind it, at minus 1, minus 2, minus 3. So, residue at minus 1, first I try to find out. So, my formula suggests it is z tends to minus 1. I multiply the entire stuff with z minus 1 multiplied by f z square minus 4 z plus 3 divided by z plus 1, here I need to multiply, because my residue at minus 1. So, z minus minus 1, so z plus 1, z plus 2 and z plus 3, z minus 1, z plus 1 will cancel out. Then I need to just evaluate this function at z equal to minus 1, that is all. So, 5 multiplied by minus 1 square minus 4 multiplied by minus 1, then plus 3 divided by minus 1 plus 2 minus 1 plus 3, this quantity. Next, it is just 5, it seems to be plus 4 plus 3. In the downstairs I have 2 minus 1, so it is 1, 3 minus 1, it is 2, so I have 2. So, upstairs it is 5 plus 4, it is 9 plus 3, 12 divided by 2, so I will have a value 6. So, my first residue at z equal to minus 1 is 6. Okay. Let me find out the other residue quickly. So, residue function of z at minus 2, which is limit z tends to minus 2. Once I multiply z minus 2, so z minus 2 will cancel out. I am not doing that part, I am just directly writing after removing z plus 2 term, which is obvious. So, I just need to evaluate this quantity, that is all. I need to evaluate this quantity at z equal to minus 2. Z plus 2 will cancel out because I multiply z plus 2 and z plus 2 is already there in the downstairs. So, now this 5 minus 2 square minus 4 minus 2 plus 3, I have this. If I evaluate this quantity as minus 2, so now it is minus 2 plus 1 minus 2 plus 3. So, here I have 5 into 4, so 20 plus 8 plus 3 divided by minus 2 plus 1, so minus 1 is here, and then 3 plus 3 minus 2, so that means 1 is here. So, I have minus 1 here, 1 minus multiplied by minus 1. So, it will be seems to be how much, 30 minus 31, 8 3 11 and then 20, it is minus 31. Minus 31 is the value of the residue at function z equal to 2. 1 is left. So, this is just a lengthy problem, but straightforward, you do not need to do the derivative of that. Okay. So, residue, finally I have to calculate the residue of fz at minus 3 point. So, again it will be just the limit z tends to minus 3 minus z plus 3 will cancel out. So, I have 5 function, whatever the function is given, 5z square plus 4z plus 3 divided by z plus 1 and z plus 2. This 2 term is in my hand, and then I put the limit directly. If I put the limit directly, then I have 5 minus 3 square minus 4 minus 3 plus 3 divided by minus 3 plus 1 minus 3 plus 2. So, it is 3 9, so 45 minus 12 plus 3 divided by this quantity is minus 1, this quantity is minus 2 multiplied by minus 1. So, we have 2. So, 45 plus these things it is plus. So, 3 into, so it seems to be 45 5, so it is 60 by 2 seems to be. So, I will have 30. So, the residue of this quantity at z equal to 3 is z equal to minus 3 is 30. Okay, so we have few straightforward thing. So now I have another kind of residue, and this residue is something. So let me check, is there any other problem? Okay, let me do once again one example before going to that. So function of z, say e to the power of z divided by z cube. This is one function. So now I can do one thing, that so far we are blindly using this residue structure. So for this particular problem we will check, because residue is nothing but the coefficient of the Laurent series, the coefficient of 1 by z minus z0 in the Laurent series. So if I evaluate this as a Laurent series, then I can have the value of the residue. So let me do that. So if I expand this as a Laurent series around z equal to 0, around this point in some limit with z less than 1 or something, then it will be z cube, and e to the power z is 1 plus z plus z square plus factorial by factorial 2 z cube by factorial 3 and so on. Mind it, singularity is at around z equal to 0. So this function e to the power z is an entire function. So there is no singularity of this. We have a singularity of z here at 0 point. So this is the point where we have a singularity. So I am excluding this point, I am trying to find out how the expansion is. So excluding this point, is the entire part, the function is analytic. The function is analytic except the point z equal to 0. So I am expanding these things in this region. If I expand, this will look like this, and then I have few terms, z cube plus 1 by z square plus 1 by 2 z factorial 2 z rather, then 1 by factorial 3, then z by factorial 4 and so on. So now you can see that this is a series where we have the principal part and the analytic part. So this is my principal part PP, 1 by z0, 1 by z minus z0. If I write it in this way at around z equal to z0 the way, so it is z minus 0 cube plus 1 divided by z minus 0 square plus 1 divided by factorial 2 z minus 0 and so on, and this is the analytic part AP. So in the principal part, this is the term which is interesting for us, because this is the term where we have a coefficient of z minus z0. That means the coefficient is 1 by 2. So 1 by 2 should be my residue. So this is the coefficient, this is eventually a minus 1, 1 by 2. So without blindly putting this formula, by just expanding, I can also find out the residue, and here in this case the residue of this function, residue of function z at 0 point comes out to be half, right. Now if I try to blindly put this formula should be here, it is written. So it has a pole at z equal to 0 and the order of pole is 3. So now I am going to use the formula and check whether both the cases I am getting the same result or not. So residue, using the formula, the residue of function z at 0 comes out to be something like limit z tends to 0 1 divided by 2 minus 1 factorial 3 minus 1 factorial d2 dz square z z cube and the function e to the power z divided by z cube. So, this is the expression if I blindly write this and try to find out the residue. So, z cube will cancel out. If I make a double derivative, so 1 divided by 3 minus 1 factorial is nothing but 2, then limit z tends to 0, this function if I do e to the power z, if I make a derivative, first derivative and second derivative, this function will be simply e to the power z. Then if I put the limit, then I will have e to the power 0, so e to the power 0 is 1. So, eventually I am having the same residue that I am getting here. So, half here half. In the first case I calculate the entire stuff by expanding these things, and in the second case I am try to find out the same thing, but here I am getting the same result and exploiting the expression that is written in that side of the board. Both the cases I am getting the same results. So, with this note I would like to conclude here. So far we know that how to calculate the residue if the function is given and its function have some finite singularity, and this singularity has some order and all these things. But apart from that, there are few other functions where this procedure may not be suitable, and in that case we need to use something different. And for example, a function fz, I am just giving you the functional form, maybe next day I will calculate that. 1 divided by sine, say sine n pi z, So, here we have a singularity at z equal to any integer if you find. So, z equal to 0 we have a singularity, z equal to plus minus 1 you have a singularity, z equal to plus minus 2 you have a singularity. So, all these singularity are here in this point, 0 here, 1 2 3, 1 2 3 minus 1 2 3 minus 1 minus 2 minus 3 and so on. So, the function is analytic in this intermediate region, and apart from that this function has an infinite number of singularity. Now, if I try to find out what is the residue of this particular function in any of this singular point, then how to figure out. So, that is an interesting problem. So, I will try to do that in the next class, because today we do not have much time to do that. In the next class we will start from here, and then we try to understand why the residue is so important in this particular case. That means in complex analysis we try to find out why it is so important, because it gives me directly the solution of a closed integral. Even if some singular point is there, I can exclude this singular point and I can find out what is the value of the integration without doing any kind of so called integration, just using some formula. So, with that note, so let us conclude here. See you in the next class where we start the residue once again and try to find out how to calculate this special kind of function, and then try to understand what is residue and how the residue is important in calculating integration. So, thank you very much for your attention. So, see you in the next class.